So we're gonna start our 9-2, which is our last section of stuff before the third test. So a couple of reminders on Friday, hopefully most of Friday, will be a review session. So whatever questions you want to ask, feel free. I don't think I mentioned this in class on Monday. I forgot, but I posted on Canvas, like on this current week, there's basically I posted a link to the review website again. A list of questions from the book that are relevant, and another like practice quiz that has like 30 something questions in it that I think are all relevant. So take a look at those. I'm willing to talk about any of that stuff on Friday, but it's also just good practice between now and Monday. Any other questions before you get back into it? Okay, so done a lot of stuff with parametric curves the last day and a half or so. Now we've kind of hopefully gotten more accustomed, more familiar with that, like that system of representing equations. We can start talking about doing derivatives and integrals with them. So let's go ahead and get started. So I believe that without me giving you too much instruction, we could find what dx dt is and what dy dt is. So let's first kind of unpack what this notation means. When you see dx dt written like that, what does that mean? So first of all, what operation does that signify? That's a derivative, right? So in a lot of cases, you can talk about derivative. You can just say the word derivative, and that's good enough. Can't really do that now because we have, there are more than two different variables we're talking about. So when I say dx dt, what am I taking the derivative of? And what? Go ahead. Derivative of x. There you go. So I'm going to take the derivative of x with respect to t. What would that be in this case? So I have an expression for x in terms of t. Can you take that derivative? 2t minus 2. So can we do something similar for dy dt? Okay, sorry. I heard something. I wasn't sure if I heard what it was. So, right. So basically, as long as we are aware of, from that Leibniz notation of a derivative, that d blank over d blank, that notation, as long as we understand what that says about what we want to find, we can just redesignate that for these parametric curves. So I found dx dt, I found dy dt. I would like to get dy dx. So that is a new thing here. So how do I find that dy dx? Well, I have dy dt. Symbolically, does this make sense? So dy dx is equal to dy dt times dt dx. Okay. Probably a more useful way to think about this is dy dt over dx dt. So now, can I put this together? Can I express dy dx in terms of the derivatives I already have? What would that be? So we said dy dt was 1, right? And what is dx dt? 2t minus 2. So dy dx is equal to 1 over 2t minus 2. Which might seem a little strange. I'm calling it dy dx, but the expression I have for it is all in terms of t. So let me ask this question, since I probably haven't asked it in a while. What does a derivative tell you about a function? Rate of change, and I think we have to be more specific now because we got a lot of stuff going on. So when I say dy dt equals 1, what does that mean about the way that those variables behave? You said rate of change, so we can build up from there. Specifically, what does that rate of change of 1 tell us about the behavior of this function y of t? You have a constant derivative, so what does that mean?
The rate of change is constant.
The rate of change is constant. What kinds of functions have constant rates of change? Linear ones, right? Does that make sense with what this thing looks like? So y equals t plus 1 should be linear. But when you talk about a rate of change, we got to be a little more careful about, rate of change always joins two measurements. Now I think we have to be specific about what those two measurements are. So this 1 over 2t minus 2, what are the two variables that this rate of change joins together? As blank changes, something else changes at the rate of 1 over 2t minus 2. That's y with respect to x. So we're kind of building these things up using techniques you've already done, but now we have to think about what the rates really say. Any questions about either like mechanically how we found these or what we actually found and what they mean? Okay. So this curve right here, and it's just one curve. I have two equations here, but just one curve. So let's take these one at a time. So first I want to show that C has two tangents at 3, 0. So how could it have multiple tangent lines at the same point? So I don't remember exactly what this looks like, but I know that at 3, 0, what must be going on is this. Probably have something like this going on where it loops. And actually at that point it crosses, for two different t values, same point, but it comes through two different times. Would it make sense that would have two tangents? Okay, how do I find those? So I know the point is x equals 3, y equals 0. Can I find what t value that corresponds to? That point. How do I do that? Okay, so I can do t squared equals 3 and t cubed minus 3t equals 0. Do I have to solve both of those? I think, well, I mean, you could, but they better give you the same information. So I think in either case, we're going to get t equals plus or minus the square root of 3. So I think that's good enough to show that this thing has two tangent lines. But now I want to find the equations of those tangent lines. So you probably have not found the equation of a tangent line since Calc 1, so let's review how to do that. How do I find the equation of a tangent line? So we're marching towards this kind of thing, y equals mx plus b. So basically what I want to do is at this point here, I want to find the slopes of the two tangent lines that come through here. So let's start there. How do I find the slope of a tangent line? Take the derivative. So we got to be more specific now. What derivative do I need to find the slopes? So yes, I need those, but okay, so let's find those first. What is dx dt? 2t. What is dy dt? Okay. Can I get the slope now? Yeah, so that's where we're going to get the slope from, because the line that we're going to build is a line that relates x and y, right? So to really find the slope of this tangent line, I need to find dy dx, which is going to be what? Very, very close. Dy dt over dx dt.
Oh.
So I,
3t squared.
yeah, I wrote them in the order that was most confusing. So that's our derivative for dy dx. I'm going to modify this question. I just want to find slopes. I'm not going to find the whole equation. I believe you could find the y-intercepts, but let's stick with slopes for now. I should have two different slopes. How can I find them? Or I guess, how can I find one of them? Go ahead.
Plus or minus 3
Yeah, so let's do that. So if I find one of them, dy dx is equal to, sorry, restricted at, yeah, pick a t value. That t equals radical 3 is equal to 3 times 3 minus 3 over 2 radical 3. So 6 over 2 radical 3. So I think that's one of my slopes, is just radical 3. How about the other one? So what other t value do I care about? Negative radical 3. And I believe that slope, the only thing that's going to change is the denominator, right? That should be negative radical 3. So any questions there? Okay, I think I gave myself another slide for this. Yeah. So I want to find where the tangents are horizontal or vertical. So what was it? 3t's. I guess I can figure it out. So here's the expression for dy dx we found. 3t squared minus 3 over 2t. So let's pick one of these first. I want to find, let's find where the tangents are horizontal. What does it mean if I have a horizontal tangent line? The slope is 0, right? So I think I can set dy dx equal to 0, right? And that should give me the t value for those points happen. So how do I solve things that look like this? If I have a fraction that equals 0, then really it's the numerator that has to equal 0, right? Or algebraically, you could multiply both sides by 2t, and that would give you this. 3t squared minus 3 equals 0. So what t value or t values am I going to get from this? T equals plus or minus 1. But I asked for points, right? So what points is that t equals 1 going to give you? More importantly, how do we find that out? There you go. So when t equals 1, what point do I get? 1 and -2. And when t equals -1, I get 1 and +2. Okay. So this is for t equals 1. This is for t equals -1. So at those points, basically those are like comes to either a peak or a valley. I have a horizontal tangent line at those 2 points. How about for vertical? What does it mean to have a vertical tangent line? Go ahead.
Wait, how did you get those points? Like,
The X and Y values for the points. So are you okay with how I found this T value, this pair of T values? So once I have these T values, like these functions, these give me X and Y values in terms of T. So I can plug in one for T.
okay, I
Or-
thought you plugged it into the original one, so dx and dy. So
Oh no. If I did that, what should I get? But I should get 0, right? Because that's how I found these 2 T values. Yeah, so if I want I mean, and this is, I'm sure this was something you all struggle with in Calc 1 because I think everyone does, is knowing like what the derivative tells you versus what the function tells you. Do I want rates of change or do I want locations? So knowing how to make that decision is still important. What else? Oh yeah, so verticality. So we talked about how to figure out when there's horizontal tangents. What does it mean if there's a vertical tangent? So basically, if your graph is the denominator is equal to 0, right? So if you have a vertical tangent, that means you have some change in y for no change in x. What's the slope in those situations? It's undefined. It can't be defined. You have a change in y, no change in x. So what causes things to be undefined? One of the ways we can talk about it. Denominator is 0. So if I want vertical tangents, I'm going to look at this. So only one t value, t equals 0. What point does that give me? The origin? Yep. Okay. So I have horizontal tangents at these places, vertical tangents at these places. Any questions about how we found all those points? Right now, I want to know where this thing is concave up and concave down. So going back to Calc 1, what tells you about concavity of a function? Second derivative. So now what I want to do, I want to find the derivative with respect to t of what? What is a second derivative? It's a derivative of the first derivative, right? So I want to find the first derivative of the first derivative. So I want to take the derivative of dy dx with respect to t, right? But dy dx itself has something to do with x. So I want to divide that by dx dt. Basically, I'm obeying the chain rule here.
wait,
So-
why are you dividing it by dx? So it can just be in terms of.
So let me build this up a different way. Is it okay if I call dy dx this? Okay. So this is a function of x, but I want to take its derivative with respect to t. So because of chain rule, it's kind of weird to think about this as chain rule because I'm kind of going the opposite way. But y prime is a function of what? Y prime is a function of x, which is itself a function of t, right? So basically, I got to build this up like. Basically, I have to multiply this by dt dx. And this will give me the derivative of y prime as a function of x. Now I'm going to rewrite what y prime is. That was the derivative with respect to t of dy dx. But x itself is a function of t, right? So I'll rewrite that as dx dt. If I can write a d. So this right here is in general the second derivative of a parametric curve. Can we do this now? What's the numerator of this thing going to be? What's that? Oh, no, I just mean, sorry, not in general, but like specifically for us. So the derivative with respect to t of dy dx. So basically, I want to find the derivative of what? 3t squared minus 3 over 2t. So that's going to be a little more involved. Dx dt should be simple, right? What's that? 2t. All right, so how do we find the derivative of things that look like 3t squared minus 3 over 2t? Quotient rule is a good way to do it. Do we remember the quotient rule? As for you go derivative of the bottom first. So 2 times 3t squared minus 3 minus 6t times 2t. All over what? 4t squared. All over 2t. So pretty gross. Can we simplify anything at all? I think the final denominator is going to be 2t. Does anything in the numerator cancel out for us? I think I'm going to 6t squared minus a 12t squared, so minus 6t squared. Is it just negative 6t squared minus 6? Okay. All right, so that's the second derivative. So first of all, any questions about how we got that second derivative? Good.
I thought the quotient rule is low derivative I minus high derivative of
Is that not what we did? That is what it is. Is that not what happened here?
Well, the first term.
Oh, you're right. Okay. So let's repair. Yeah, so it's low times the derivative of the high. So I believe that this repairs everything. Yeah, good catch. I think that is now fixed.
What is the 4t squared there?
So the 4t squared, basically the 4t squared minus divided by 2t becomes 2t. Oh, that's not going to happen, is it? Yeah, you're going to multiply it. All right. Let's keep debugging. Where's that okay now?
AT cubed.
Yeah. Okay, I'm just gonna revisit this whole thing from the beginning because I'm snake bit. So the derivative of low times the derivative of the high, so 2t times 6t minus the derivative of the denominator times the numerator. Okay, are we okay now? Looks like it. So there's the second derivative. How can I use that thing to give me concavity? Can we first talk about where the concavity changes? What do we call those things? What's that?
Point of inflection.
Yeah, inflection points, points of inflection. Where do points of inflection happen? Where the second derivative is equal to 0 or so, and typically that's Typically where that's where the second derivative is 0 or where it fails to exist. So I don't think the second derivative is ever going to equal 0. Because I don't think it's possible for the numerator to equal 0. But is it possible for the second derivative not to exist? What's going to have to cause that to happen? T equals 0 is going to cause the other concavity not to exist. So let's do this now. Let's pick a negative t value and a positive t value and see what the concavity looks like. Pick your favorite negative number. -2. So t equals -2. What does that mean about the second derivative? D squared y dx squared equals what? 30? So what does that mean about our function? Concave up. So if actually it's going to be 30 over whatever the denominator is. But that is going to be positive, right? So we have concave up for negative values of t. How about for positive? Oh wait, no, that's going to be what's happening to me today. It's going to be concave down, right? All right. So that's going to be concave down for t less than 0. Do we agree it's going to be concave up for positive t values? So I know I have my mistakes have probably confused people, but let's try to get it back. Any questions about anything that we've concluded here? Go ahead.
Negative t, you just plug it into this equation and you just got.
Sorry, the second derivative. I couldn't tell what you were pointing to, but this thing here. Yeah.
You just
So-
put -2 there.
Yeah.
Oh,
So if you plug in -2 there, so no matter what you plug in for the numerator is going to be positive, right? So the positive or negative is all going to come from the denominator. Cubing negative numbers gives you a negative number. Cubing positive numbers gives you a positive. So I think this thing is concave down for negative t values, concave up for positive t values. Can't talk about its concavity at t equals 0. So big things I want to focus on here is basically how to use the first derivatives, how to find and use the second derivatives. Basically what kind of questions those things answer. Any questions here? Okay. So parameters not always t, but I still have a parametric curve here. So I want to find the tangent to this cycloid. Basically, what these things look like is something like this. I don't think you need to know what this looks like to answer this question, but might be helpful. So X and Y, this thing I believe sort of looks like basically just these like equally sized half circles all laid out end to end. So I would like to find the tangent to this graph, and I'm giving you a theta value. So how can we find that? Or what kind of things do we need to find to get there? So maybe let's work from the end backwards. If I want to find a tangent line, I need a derivative, but specifically what derivative do I have to get? dy dx. So that's where I want to go. I don't think I can get that yet. So what other things do I need? Close. We're not calling it t this time. It's not r. Theta. Yeah. So these x, I'm going to say these are functions in theta. What is the r? The r is basically the r's and tell you what the radius of those circles are. But let's see what happens to them when I start taking derivatives. So what is dy d theta? So for now, we can treat r as a constant. So what's the derivative essentially of 1 minus cosine theta? Positive sine theta. So that's, let's be very clear, this is dy d theta over dx d theta. We said r sine theta. What is dx d theta? R times something. 1 minus cosine theta, which means dy dx is equal to sine theta over 1 minus cosine theta. No? Okay. So I believe that's a good expression for dy dx. What do I want to do with it now? What am I really asking about? Plug in pi over 3 to my dy dx. So when theta is equal to pi over 3, what do I get? I get sine of pi over 3 over 1 minus cosine pi over 3. Is that radical 3 over 2 over 1 minus a half, 1/2? So it should come out to radical 3. This time I'm going to ask us to find the full equation of the tangent line. So that radical 3 is what? What did we just get? That's the slope, right? So if I'm trying to get an equation of this form, y equals mx plus b, we got the m, y equals radical 3x plus b. I got to solve for b. So what other information do I need? Plug in rad 3 for x?
Or no, plug that into the equation. Or actually,
So yeah, I think I need more information to isolate b. Can I get like a corresponding xy value? So we know that the tangent at some point is radical 3, right? But I don't think we know where that point is yet. Can we get where that point is? What's the x value of that point?
R comes direct.
So to get an x value, I can use the parameter. What is the sine of pi over 3? Radical 3 over 2. Well, this is going to be really inconvenient looking. So r times pi over 3 minus radical 3 over 2. And what's the corresponding y value? R times a half. Okay, I'll just leave it like that. Does this get simpler or is it going to be really gross? Let's see. So 1/2 r equals radical 3 times r times pi over 3 minus radical 3 over 2. Plus b. Will I rob you of your closure if I don't get that nasty long exact expression for b? Question. Yeah, we can use point slope. Would that make this look even nicer? What's point slope form look like? Yeah, that's going to be much preferable here. So what's our y1? So y minus r over 2 equals radical 3 times x minus r times pi over 3 minus radical 3 over 2. So we'll leave it like that. That's better. How are we doing? Can we find where the tangent is going to be horizontal? Where's the tangent going to be horizontal? Where's that? Where slope equals 0? Tell me if you agree with this. Is this good enough? Can I say dy d theta equals 0 to find where it's horizontal? I don't think we said it like this last time, but that's essentially what we did. Because we really want dy dx to be 0. But I think that's going to happen where the numerator of that derivative is going to be 0. So what is dy d theta? R sine theta? Where is that going to happen? It's going to happen in infinite number of places, but can I like generalize where that's going to happen?
Sign 0 and sign -5.
So it's going to be any multiple of pi, right? So I'll say 0, theta equals k pi, where k is, have we seen this symbol before? That means the set of all integers. So as long as k is an integer, basically any integer multiple of pi is going to give you that. How about where the tangent is vertical? That's going to come from dx d theta equaling 0, right? And we said that was r times 1 minus cosine theta. So basically the question we're asking is this: where does the cosine of theta equal 1?
Also multiples of 5.
I don't think there's going to be multiples of pi. Not all of them anyway. Multiples, yeah, it would be multiples of 2 pi. So we have a little bit of a problem, right? Because I think we're saying that. So let's say at like 5 pi, or no, like at like 6 pi, we're going to have both a vertical tangent and a horizontal tangent. I don't think that can make sense. So let's go back to dy dx. Dy dx is this thing here, right? So let's talk about what happens at like 6 pi. What's the sine of 6 pi? 0. What's the cosine of 6 pi? 1. So we get 0 over 0, right? But I don't think that we can't say dy d theta is equal to 0, right? Because the whole thing just doesn't. We can't say dy dx is equal to 0 because the whole thing's undefined, right? So I think we can repair this by doing this. I'm going to say this is equal to it's odd multiples of pi, right? So I'll say 2k plus 1 times pi. So one thing to look out for when you're finding these horizontal vertical tangents. Yeah, you want dy dx to be equal to 0 to get a horizontal tangent, but make sure that make sure the dx d theta on its own is not 0. Make sure you actually have a well-defined 0. So based on this graph we did, where are the horizontal tangents going to show up? So if we just think a bunch of half circles laid out next side by side like this, where am I going to get the horizontal tangent? So the 0 slopes. It's going to happen at the peaks, right? And those are going to show up in regular intervals. Where am I going to get the vertical tangents? Like these cusps right here, right? So those are, if I were to draw this thing totally to scale, those happen, like they alternate. So every pi, you'll get one to the other. How are we doing? Go ahead.
Is dy over d theta the horizontal or vertical?
Good call. I'll clear that up. So what do we think it is? If y is not changing, is that a horizontal tangent or a vertical tangent? That's horizontal. And if x is not changing, but y is, that'll be a vertical. Good question. What else? Go ahead.
Why in the last step did you just like for dx over d theta, you did cosine theta equals 1.
So
But for dy, you didn't cosine the theta.
so sine of theta equals 0 for this one, right? So there's some stuff I didn't write down because I was running out of room, but what angles give you a sine value of 0? If there's any room left, let me squeeze in the unit circle here. Sine values come from like where the y values, what the y coordinates are of the unit circle, right? So where is the y coordinate going to be 0? At this point and this point. So 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, and so on. And then basically I saw them setting r times 1 minus cosine theta equal to 0. So here's the stuff that I did not write down. If you divide both sides by r, you get 1 minus cosine theta equals 0. And then if you move cosine theta over, you get cosine theta equals 1. So that's how I got to the equation we ended up dealing with. All right, anything else? Okay. Okay, now I want to find area. So same equation, same curve, except now, so I guess I'll recreate this drawing. I want to find the area underneath one of these. How do I find areas under curves? Integration. So typically, what do those integrations look like? So this is the x-axis, this is the y-axis. I want to integrate over some bounds. I want to integrate some function with respect to some variable. So I got a lot of blanks to fill in. So how should we attack this thing? What kind of, if we're going to set up this integral, what kind of blank, are there any blanks we can kind of fill in off the bat? Maybe it's easier to think about what we typically do. Typically we go from one x value to another. We integrate some function of x with respect to x, right? But let me ask you this, f of x is a value of what? Of what? Not usually. It's a y value, right? In our case, the functions are written in theta. But typically what we do when we're finding an area is, let's go back to probably the end of last semester. When you're thinking about areas under curves, the first thing you were probably taught was to chop this up into a bunch of rectangles, right? How do you find the areas of rectangles? base times height. So basically change in y times change in x. So how do I write that out? I'm going to integrate some y value times some small change in x. But don't I have those things now in terms of... So I have y in terms of theta. I have dx. But what does that dx really mean? I really want this thing to be in terms of, I want to take this integral with respect to theta. So let's represent this integral this way. I want to integrate from some a to some b of y as a function of theta times dx d theta times d theta. So basically, if I have a parametric curve, which I do, I want to integrate the whole thing with respect to that parameter. So any questions on the setup here? Basically, we're doing what we've always done. We're integrating some function that tells you y with respect to x. It's just now those y's and x's are all kind of governed by theta. They're all expressed in theta. So let's worry about the bounds last. Do I know an expression for y in terms of theta? What is it? R times 1 minus cosine theta. Can I get this dx d theta? We already got it. What was it? Okay. D theta. So that's the thing we're going to integrate. But I want to find the area of exactly one arch. So now I need to figure out what my bounds are going to be. How can I figure out what these two bounds are going to be? So basically, how to find this value A and this value B. Why are you saying y equals 0? Yeah, so basically I'm looking at where it's going to, when it's going to leave the x-axis and when it's going to return. So where does r times 1 minus cosine theta equal 0? I think we just solved something like that, right? And really, I just want to find, any two adjacent values where it's going to happen. How do we feel about 0 to 2 pi? I think that makes sense. So now, here's my full integral. The integral from 0 to 2 pi of, let's combine some stuff. So 0 to 2 pi of, I'm going to go ahead and pull out the r squared, because I told you that was a constant, times 1 minus cosine squared of theta. No. 1 minus cosine theta all squared, d theta. So I think I'm going to stop there. We're going to evaluate the integral next time. It just takes a bit to get to the end. But we have a minute left. Let's talk about the setup. So basically, in general, how do we feel about the idea of setting up integrals like this and modifying that for a parametric curve? And in particular, are we okay with how we got to this integral to find that area? So if you're good with that, I think that's a good place to end. We'll evaluate that next time and finish out this section. All right, see you all Friday, or I'll see you upstairs in a bit.